Okay, let's get back to the class. So during the break, one of the students is still got a little bit confused about the discussion from left-hand side to the right-hand side. So especially this. So I think maybe let me explain furthermore about this sentence. So here we mentioned that we use the pigeonhole principle to say that basically, let's say the X contain at least like K plus one of V1, V2, etc. to V2K plus one. Then this basically this implies that at least two of them are adjacent, or maybe let me actually draw like this. So at least two of them are adjacent. So we just think about this. I mean, maybe we have like maybe like the the smallest, maybe it's just like VI1. So the next thing, so if none of them like the pair is adjacent, so the next should be something like VI1, like the, maybe let's write this. VI2, where like I2 minus I1 is larger than 2. And basically I3 minus I2 is larger than, so VI3, VI4, etc. But this is just impossible because you just consider, I mean, you can K plus one, VIK plus one. And basically here you have IK plus one minus IK is larger than 2. So the only way that you make this possible, I mean, is like I1 equals to 1, I2 equals to 3. I mean, on the other hand, because you only have like a K plus, the upper bound of the i's here are 2K plus 1. The only possible way that you make this is possible is like IK equals to 2K plus 1. But we know that actually the first vertex and the vertex that 2K plus 1, they're adjacent. So this is just like by a slightly more detailed argument, you can see that basically you have like a cycle. Basically, you have this kind of a cycle of like a number of vertices beyond 2K plus 1, and if you want to take K plus 1 of them, then at least 2 of them should be adjacent. So this is just a further explanation about like the left-hand side to right-hand side. Let's basically finish the proof from right-hand side to the left-hand side. And actually, the proof is basically nearly finished. So we have the discussion here. We have this contradiction argument saying that basically, if there is actually an edge in the same layer, then this is just this assumption that the graph does not contain an odd cycle. So basically, we have this. And actually, as a result, so because we have a no edge in the same layer, I think it is very easy to see that a very valid partition is S going to be the union of L0, of L2, L4, etc., and Y is going to be a union of L1, L3, L5, etc. Because you are actually consider like a layers like with difference at least 2 each time. So there are just like inside each inside X and Y, there just cannot be edges between like different layers. And we prove that there is no edge inside the same layer. So we are actually sure that this XY gives a bipartite partition. Okay. So this basically completes the proof, both the proof from the left-hand side to the right-hand side and also from the right-hand side to the left-hand side. And I think basically from this discussion, basically the way that we use the BFS, a remark we can see is that basically BFS, let me actually get back to the black color. BFS actually gives an algorithm that determines bipartiteness in O(n) plus n time. So if, for instance, if G is not bipartite, then basically from this argument, we can see that then there exists an edge in the same layer. And basically, we have the adjacency list representation and checking all edges in the adjacency list. Takes time. OM to determine whether such an edge exists. Okay. So this basically finishes the discussion about the bipartite graphs, and basically the very important criteria that a graph is bipartite if and only if the graph does not contain off cycles. And actually deciding whether the graph is bipartite or if the graph is bipartite, you can find such kind of a bipartite partition. It's also going to take time O of m plus. So is there any question about like bipartite graphs? Okay, so the last thing that we are going to introduce, I mean, we are talking about different kinds of graphs. So the last thing that we are going to introduce are directed graphs. So actually you see that we have been talking about undirected graphs. I mean, in general, this kind of like UV edge, we don't have like a direction, like whether a U is going to V or V is going to U. But actually in a lot of scenarios, we do want to study directed graphs. So maybe let's do everything more formally here. So definition. So we consider a graph G. Also, we have a vertex set and also an edge set. So we write edge UV as it actually goes from U to. Maybe let me actually write this U more carefully to distinguish between U and V here. So for instance, maybe we can consider like a web graph. So I guess in general, I mean, this is really not something, I mean, like, yeah, because we have like, for instance, hyperlinks point from one page to another. And this is really like a one direction like point. So you see that for some real applications, when we want to consider graph, it really makes sense that we want to consider some directed graph. So maybe, for instance, when we want to draw a directed graph, it is probably, maybe this is just like a random graph that I'm drawing here. So in general, like a directed graph is going to look like this. So similarly, because we have been talking about like the ST connectivity problem, also like the problem of finding the shortest path, we can of course define like a similar problem that, for instance, we can consider like a directed reachability. And also that ST shortest path. So here, I guess the intuition is relatively straightforward. It's just that we want to given a node S, find all nodes. Triple from S. And similarly here is that given two nodes S and T, so we can consider the shortest length from, it's here we want to be careful. It's not like between S and T. This is going to be weak in terms of directed graph, but we are actually going to write what is the length of the shortest path from S to T. So I guess these are relatively straightforward definitions. So here we can still discuss about connectivity, but here we have like a further definition called strong connectivity. So for strong connectivity, we say that a graph is strongly connected. If for every pair of U and V, there is a path from U and V and also a path from V and U. Oh, sorry, from a path from V to U and also a path from U to V. It's basically we want to have the things both sides. Okay. So I guess we can, after we have been discussing about like the connectivity, like the shortest path problem from undirected graph, I guess there are some relatively easy observation that we can make. So for instance, a lemma that we can give here is that maybe we consider like any node. So like S be any node. So G is strongly connected. So if and only if. So in this class, so basically we write IFF should be if and only if. And this is also a standard like abbreviation, for instance, like the WLOG without loss of generality. So this is something, a standard that we use throughout the proof. So if and only if every node is reachable and S is reachable from any node. Right. So in general, this just means that if we want to consider the strong connectivity of a graph, it suffices that we consider like a certain fixed S that we want to see like whether all vertices are reachable from S, and actually all vertices we can reach S from all vertices. And I think this is also a relatively straightforward because one direction is just trivial according to the definition of strong connectivity. And the other, I think, for instance, assume that you want to, you have such kind of an S, and maybe you want to consider like a path from U to V. You just like concatenate, like US, and because you assume that like actually from U you can reach S, and from S you can reach V. And of course, on the other hand, like from V to U, you just concatenate like to S. So here in general, we allow like overlaps between paths. So in the concatenation, maybe along this way, along this path, maybe some of the vertices they overlap, but this is not a problem according to the issue. You can make this kind of concatenation here. So I guess can see is that in general, we want to consider this kind of the running time of determining such kind of strong connectivity. And basically based on the lecture today, I guess it is also natural that you can imagine that this is probably going to take time O of n plus n, and this is actually the case. So, oh, sorry. Just, so there's an algorithm. Sure. If G is strongly connected in O of n plus n time. So the algorithm is actually relatively straightforward. It's just some, maybe we have this kind of bound like O of n plus n. You just want to think about like BFS is really our friend today. So you just want to have a good way to actually utilize the BFS algorithm. So we can consider something like this. We pick any node S. So we run BFS on S in G. So actually there is a directly like you can directly find a version of BFS for the directed graph. I mean, in general, you look at this BFS algorithm. I mean, if you just each time you consider each edge, you consider each edge UV here, you just like consider all the directed edge here, just like from U to V here. I guess this is actually transparent that using such kind of this definition of the BFS is just going to be applied to the directed. And basically for this directed graph, I mean, in general, we applied here that we pick any node S here and we run BFS from S in G. And also on the other hand, we can run BFS from S in G reverse. So G reverse is, let me write in a red color here. So the G reverse is the graph that reverses the direction of all edges in G. And we actually the algorithm return true if all nodes are reached in both BFSs. So I guess the correctness and also the time analysis at the big O of m plus n, the time complexity just like follows directly from the fact that we use BFS here, and also the correctness is basically you want to consider the reachability, and also based on the lemma here that basically we reduce the problem of strong connectivity to finding like basically the connectivity with respect to a specific point S. And basically each of these both of the BFS, and actually one of them is deciding whether all the nodes is actually reachable from S, and the other basically this BFS on the G reverse is deciding whether like every node can reach S. So basically, I guess the correctness and the complexities is basically transparent from the previous discussion. So any questions? Basically about like the introduction of the directed graphs here. Okay, so let's move more into definitions of directed graphs. So more details. So for undirected graphs, so let's think about like the beginning of this lecture. I mean, at around 3 p.m., the first thing that I was talking about were graphs. So basically, the trees. I mean, the basic definition is a tree. So we can consider some sort of tree also in a directed case, although we are actually going to be a little bit more careful. So when we talk about the trees, I mean, the trees in the undirected scenario are basically connected, but cyclic graphs. So here we are actually going more into this kind of definition that we basically consider graphs that basically have no cycles. And this actually is going to give us a new definition. So directed acyclic graph, and typically abbreviated as DAG by the first letters, is a directed graph without direct cycles. I mean, by direct cycles, it's just like, for instance, oh, this graph does not have any cycles. Oh, it has, sorry. This is a directed cycle. I mean, you just consider the going of the directed edges, and it makes if it makes a cycle, it's called a direct cycle. But here we want to be careful because when we want to talk about the trees, I mean, undirected graph, I mean, undirected trees, actually the structure of the trees is actually quite transparent. At the beginning of the class, we talk about this kind of 3 criteria. But here, actually, we want to be careful that DAG can have much more complicated structures. So for instance, maybe let's take a look at this graph. A graph with 4 vertices. So maybe we have this edge, this edge, this edge. So for this graph, actually, every pair of VIVJ, there is an edge. But actually, this graph, we think about the cycles here. So this graph has only 4 vertices. So we only need to be careful about like cycles of length 4 and also cycles of length 3. So basically, this graph has no cycle of length 4. And this can be easily observed because we cannot enter V1. So if there is a cycle that actually visits all of the V1, V2, V3, V4, but which point there is no edge that can actually go into V1, and actually all the edges, and actually we have V1 to V2, V2 to, oh, sorry, V1 to V2, V1 to V3, and also V1 to V4. So just from this, we cannot have any cycle of length 4. And furthermore, there is no cycle of length 3. So due to the same discussion, there's if there is a cycle of length 3, it shouldn't contain V1. But also furthermore, there is not a cycle between, among, I would say among V2, V3, and V4, because if you look at V2, V3, and V4, this is not a cycle. So this just implies that this graph is DAG. So you see that if you want to consider like a cyclic graph, this is really a significant difference between undirected graph and directed graph. And in general, we want to be careful. And actually, you can imagine that such kind of DAG is going to have more complicated structure. So this is actually, this intrigues me. I mean, I really want to give good algorithm for this. I mean, whether we can give a good characterization of the DAG or not is actually going to be an interesting problem. So here, before we introduce like a precise characterization of DAG, maybe let's give some further definition to actually to characterize this and make everything more formal here. So the thing that we are actually going to introduce is called a topological order. So this is actually going to be an ordering of the nodes of a graph. Or I should say a directed graph. Such that for every edge, Vi, Vj. So we are talking about the vertices, Vi and Vj. This is basically why we call this an ordering. So basically we number all these vertices, I mean, 1, 2 to n, and basically we have this corresponding ordering. And it is a topological order if for every such kind of edge, we have I smaller than j. So such kind of topological order, I mean, this definition might sound a little bit artificial at the very beginning, but maybe we want to consider something, for instance, like a course prerequisite graph. I mean, this is very naturally a topological order graph because in general, I mean, of course, Vi must be taken before Vj. We just consider this kind of things, and maybe let's also, on the other hand, consider something like paper citing graph. It's just like later papers. I mean, I would say like only later papers can set early papers. It just means that there are very natural scenarios in general we can consider such kind of topological order. So you see, like this topological order is really something, I mean, it has this kind of strict order. I mean, if all the edges, I mean, you consider all these kind of directed edges on Vi to Vj, we are always going to have I smaller than j. You see that this is probably something going to have some similarity to DAG. And actually, this is something we want to prove. A theorem here that if G has a topological order, then G is a DAG. So this is relatively easy to be observed if we also we prove by contradiction. So we suppose the contrary, let's say. If we suppose the contrary, then basically G has a topological order. Let's say the topological order is V1, V2 to Vn. And G also has a directed cycle. So here we consider this. So we consider Vi to be the lowest index node in this cycle. And we let Vj be the node just before Vi. So we clearly see that this actually gives an issue here because we are talking about a cycle here. We are talking about the Vj, the node just before a Vi here. So we actually know that Vj, Vi is an edge. But by our choice of I, because we are choosing the Vi to be the lowest indexed node in this cycle, we actually by assumption we have j smaller than I, contradicting to the topological order assumption. Any questions? Yeah, I think this is relatively easy to see. And of course, I think since I'm proving a one-hand thing, I mean, if G has a topological order, then G here is a DAG. Of course, we want to consider the other way around. And actually, this is also correct. But actually, to do this, I mean, this proof is not so directly work. And actually, we want to prove something in the middle. And actually, maybe let me not to be cautious, not write a theorem here. But actually, the first thing that we want to prove is that if G is a DAG, then G has a node with no incoming edges. So this is the first thing that we want to prove. So let's do this. So we are also going to prove by contradiction, because as you can, for instance, see about this theorem, I mean, from topological order to DAG, this contradiction argument really makes everything quite clear. So here for this lemma, we are also going to make a contradiction argument. So let's say we suppose the contrary. So that means that G is a DAG, and every node has at least one incoming edge. So let's just maybe pick an arbitrary vertex. Pick any node, Vi1, and because every node has at least one incoming edge, so we can do such kind of things. So we basically begin following edges backward. From Vi1. So by our assumption, you should be able to find like a vertex Vi2 that actually has an edge to Vi1. But actually, you can continue doing this. So basically, you are going to have like edges like Vi3, Vi2, Vi4, Vi3, etc. So until, because this, you cannot do this like infinitely because we have a finite graph. I mean, we only have a finite number of vertices. So it must stop until we actually visit a node Vik twice. So let's take a specific look at this. So let's think about what is the scenario that is going to happen. So we have like a Vi1 here. Actually, Vi1 is actually going to be reached by Vi2 and da. So maybe let's just say, as actually notated above, that the VIK is a node that we until we reach that. So in that case, it is probably going to be originally maybe it is going to be some VIK plus 1 and maybe VIK plus 2. But actually it is because we reach VIK again. So basically it is going to have such kind of an edge. But this actually gives a contradiction. But actually let's see denote the sequence of nodes encountered between visits to VIK. C is a directed cycle contradiction. Basically contradicts with our assumption that the graph G here is a DAG. Any questions? Or student mentioned what is like a difference between theorem lemma in this statement. So lemma is more like a technical thing that we want to use because here, I mean, we have this some discussion that if G is a DAG, then we have a specific property that G has a node with no incoming edges. This is in general quite specific, but in general, if you consider like two general properties, I mean, topological order and DAG and their equivalence, I mean, this is probably more as significant than theorems. In general, I mean, I'm probably in this class going to use like theorems, lemma, maybe occasionally propositions, but in general, theorems should be at higher level than lemmas. And I think the theorem is higher than proposition. Proposition is higher than lemma typically. I mean, this is also true in writing academic papers. Okay, so this gives a lemma that we show this, and basically we are going to use this lemma to prove the other thing that we the other direction that we want. It is this time is going to be a theorem. So if G is DAG, then we can find a topological order. And actually saying like finding a topological order, this is really something constructive. And I think it makes sense that we want to think about an algorithm that can figure out a topological order. Actually, we show that this can be found in actually OM plus N time. So we consider such kind of algorithm. So we find a node with no incoming edges and order it first. So this is just directly addressed by our lemma because we have shown that if a graph is a DAG, then this graph must have a node with no incoming edges, and there always is such kind of a node. And we delete order it first. Maybe let's just say it's like a denote first. So we are actually going to delete E from G, recursively call the algorithm. Topological order, but since we have deleted this like the node with no incoming edges, so this is going to be G over B. So we are going to take this away, and actually after we have called this algorithm recursively, we append this order after B. So basically, as proved in this lemma, you can imagine that this no incoming edge vertex, this should be really like the very the vertex that should be appeared at the very beginning to make sure that there is no further edges to actually break the topological order this kind of argument. And actually, we are going to show the basically both the correctness and also the complexity analysis of the algorithm. So let's first discuss about the correctness. So because this algorithm, we do this algorithm in a recursive way, it makes a lot of sense that we need prove this by induction. So this is, of course, true if n equals to 1. And let's assume the correctness. N minus 1. So this basically is saying that given a DAG on n nodes, n larger than 1 nodes, find a node we with no incoming edges. So here we notice that the G minus V here is a DAG. It's just deleting a vertex. Does not create new cycles. So this is something we are pretty sure about, that deletion does not create a new cycle. And after having that, I mean, after we delete that, the good thing about the induction is that we can use this to promise that G minus V actually has a topological order. So I think as we discussed, it's just like we place a V first in the topological ordering and append nodes in topological order. This is valid since V does not have incoming edges. So this basically gives the correctness, and the remaining thing that we need to prove is the complexity. So we can consider such kind of observations. So we maintain the following information. So for each node here, so basically we define something we call like the count. So because here it is very important that we keep track of the node that does not have an incoming address. So for instance, like you consider a very brute force way to run the algorithm. I mean, if you don't have like a good data structure, you can still each time you just like brute forcefully check the incoming address and all like incoming address of each vertex, and by the correctness of the lemma, you are always going to figure out such kind of node. But if you just do this in like a direct way, this is not going to give you a very efficient algorithm if you like start over each time again to check like the incoming degree of the nodes. So basically here, when we want to consider the complexity, and in general, I mean, if we want to find a good topological order here, we are going to maintain something. So the thing here that we are going to maintain count is that we are going to the remaining number of incoming edges. And also because we need to call this algorithm recursively, and there are some maybe remain vertices, so we want to be careful, and we need to maintain this set of remaining number incoming edges. So initialization is actually quite straightforward when we want to consider such kind of things. So this cost is just O(n) plus n. We just like at the very first time, I mean, we at the very beginning, we probably need to start over and actually make a full scan. But in general, we can do this via like a single scan through So we can clearly see that the cost of this is actually O of m plus n, because you really need to check all the edges to actually give a correct calculation about like what the count here is. And actually you need to, because this count is we need to, for each node we need to define such kind of an array. So basically this also gives you an ON cost. So that is the reason why basically this initialization is going to give you a cost of O m plus n. But after that, maybe you can easily see that the updates are relatively straightforward. So to delete we here, because we want to take a double look of the algorithm here. So the main thing that we need to give a very careful maintenance is that the algorithm is calling recursively, and we are keeping deleting the vertices, and each time it does not have an incoming edge. So basically, the most important thing is about the update, about each time if we delete a certain vertex v here, what is going to happen. So here is that we are going to remove v from S. So basically we actually, oh, sorry, I think here I made a typo here. The S here is not the set of remaining number of incoming edges. It should be the set of remaining vertices. Well, I think I used the nodes here. Yeah, sorry for the typo. Yeah. So here, we think about what we want to work here. So basically, each time we delete a v here, we of course, because we are deleting that, so we need to remove v from, sorry, what I'm writing here. We need to remove a v here from S. And after doing that, a very important thing is that we need to give we need to make some correction into this array. I mean, basically, we are changing the count here. So we do this. So we just decrement count and W for all edges from V to W. And actually, we this W. So this is basically the thing that we want to think about. So we think about what is the influence about like, because we really want to characterize the vertices that does not have incoming edges. So we delete the V here. So basically this is going to influence, I mean, the value of count for some of the vertices here. I mean, we just like consider how this is going to be influenced. All the possible way that is going to influence this is that the edges at V is to some of the vertex, and actually the count value of this kind of vertex is going to decrease by 1. And actually, due to the lemma here, we are actually pretty sure that each time you are doing this, you are always going to have a vertex that is actually the count value is going to reach 0, and we are just like mark that. I mean, by mark that, you can just imagine that array, maybe the array does not only have 1 entry, but maybe has 2 entries. And this just increased the cost maybe by another n, but it's still under control of the big O here. So each time you are going to have a marked item, and you just like, if it hits 0, you notice that, and this just like takes O1 time per edge, and overall ON to maintain the array. So you just imagine that when the deletion happens, I mean, it's really like the update is going to take time, and actually remove V from S. This is just one step. I mean, actually, the main thing that happens is that how many times that we decrement the value of this kind of count W. And actually, this can happen at most, basically, this takes time at O1 for each of the edge, and the total number of edges is M. And basically, that means like the total cost that you are going to use actually for this decrement command is actually going to be at most a big O of M. And overall, the complexity of the algorithm, I mean, as I just mentioned, you need cost ON to maintain the data structure, but the overall cost is going to be O of M plus N. So question ended. So there is a question saying that what does it mean to scan through the graph? So scan through the graph is just mean that at the very beginning, you need to know what is the value of the count V here, because at the very, you need to know this at the very beginning, and you need to iterative through this. By scanning through the graph, you just like brute forcefully check all the edges. So we as I'm discussing here, so basically we always have this adjacency list representation. So we have this adjacency list representation. We just go through all the lists, and go through all the lists. You just like go through all the edges, and going through all the edges, you will know the corresponding value of the count, because each time you count edge like from U to V, you just increase the count V by one, and just like go through. This will help you actually go through all of the edges, and just by doing this, you will finish the construction of the count V. The count array. So any other questions? Okay, so this basically finishes the lecture today, and I think we basically have 5 minutes to recap and basically think about what we have been discussing today. So in today's lecture, we cover basically a lot of different perspectives of the graphs. So at the beginning, we basically have a good understanding about like what trees are. And basically having an understanding about what trees are, we talk about some further definition about like connectivity, like traversal, and we talk about very helpful methods like the BFS and DFS. So basically, BFS can directly solve the shortest path problem. And actually, and also BFS, as later discussed, can in general have a lot of applications. And DFS is in general also of general interest, but I think from the algorithm perspective, maybe you can see that BFS is actually clean and has wide applications. So after having that, we talk about some specific kinds of graphs. So for instance, we talk about the bipartite graphs. And we know that bipartite graph, for instance, like in matching and in a lot of applications, it just appears very commonly. And we mathematically gave a proof that for bipartite graphs, and actually a graph only if it does not contain off cycles, and basically deciding whether a graph is bipartite or not, and actually finding if it is a bipartite graph, and finding such kind of partition can be finished in time O of n plus n. So this discussions about like undirected graph, and at the end of this lecture, basically for the last hour, we also talk about directed graph and also some basic definitions such as a connectivity. And then very importantly, I mean, we want to have some definition about like a cyclic graph. And we notice that this is not as simple as like the trees in the undirected case, but still for such kind of graphs called the DAG, we can still have a good characterization, which is basically the topological ordering this kind of definition, and also this kind of topological ordering can be found in time O of n plus n. So this basically finished like the basic concepts of graphs. And in next lecture, I think gradually we are actually going to get into more like ideas and basically some thoughts about like designing algorithms. So the next class, we will talk about greedy algorithms. So in general, basically using like a greedy way can give you good algorithm. And I think because we have been talking about graphs, like basically for this whole lecture for 3 hours. So we will basically for next class, we will focus on some very important greedy algorithm on graphs, and basically give you like gradually give you some ideas about in general, what is some good idea, for instance, like greedy algorithm or some great thoughts to give a very efficient algorithms. Okay, so this ends the lecture today, and thanks for your attention.